Hello, everybody. So I'm Ra'i Gopher. I'm one of the co-founders and chief strategy officer of Tomorrow.io, and I'm really excited to welcome you to our webinar. So today we'll talk about Beyond the Data Gaps Continuous Global Sensing with Tomorrow.io Microwave Sounder Constellation. Quickly, just introducing the speakers. So as I said, I'm Ra'i Gopher. With me today, we will have Joe Munchak, who is our VP of Mission Science, Ryan Honeyegger, who's our team lead of data assimilation, Cesar Benetti, who is our solution engineer, and Ari Davidov, who is the director of international government development. We're very excited to talk with you all today and share with you some of the latest and greatest updates from our constellation development. What you'll walk away with today are 5 things. Number 1 is you'll understand the vision and the introduction to the constellation, which I'll cover in the next few slides. And from there, we'll dive deeper into the satellite technology by Joe Munchak, talk about the data products and validation with Ryan Honeyegger, talk about access and partnership models with Cesar, and second part of that with Ari. All right, so I guess to start with, it's always important to zoom out and understand why commercial microwave sounders matter now. The number 1 reason is that, microwave sounders really have been the backbone of national weather forecasting systems for many decades now, and they provide the majority of the data that feeds into numerical weather prediction models all around the globe. However, the handful of microwave sounders that we have on orbit today all belong to, other than those from Tomorrow.io, all belong to government agencies, and many of them are aging or have already reached their end-of-life period. And so in the next, actually over the past year and in the next few years, we're expecting to see quite a few of these microwave sounders going basically offline and reaching their end of life. And there aren't that many new ones being built, definitely not at the pace of that we're losing the old ones. And so we have this data gap that is actually going to grow. At the same time, we have a really severe gap in ground-based infrastructure, namely radars. And we have roughly 5 billion people around the world today who live outside of radar coverage or at least reliable ground-based weather radar coverage. Now, when we think about microwave sounders, traditionally we don't think about them as a radar replacement or radar supplement, but that is mostly because the revisit rate that we achieved up until now with microwave sounders from orbit was too low to provide any useful information in the context of precipitation analysis in real time or for nowcasting purposes. However, with our constellation, that is definitely changing because we've launched so many of those, and as you'll see in the next presentations, that we're now able to achieve sub-hourly revisit rate, which makes our data very useful and very relevant also in the context of real-time precipitation data and nowcasting products. And then last but not least is the kind of growing demand from the weather models for more data. We see AI weather-based models coming in very rapidly. And those models, and also the numerical weather prediction models, the traditional ones, can feed and actually need much more data in order to prevail and in order to do better. And so we are now providing them with this food, with this weapon they can use to become much better. So what is our constellation at a high level? You can see kind of a cool animation here. This is showing both our radars and our sounders. Today, the focus will be on the sounders, but we provide full atmospheric scanning with cloud penetrating capabilities. The frequencies we operate at are actually designed to penetrate through clouds and see all the way to the surface. They're purpose-built for weather, of course. These are not imaging satellites or anything like that. They are providing global coverage, so they have orbits that essentially see the entire globe, and with very high revisit rate and low latency, meaning that we see every point on Earth roughly within every 1 hour, and then we drop the data from our satellites to the ground shortly thereafter, within minutes. And all of this is designed to help us provide actionable impacts. And so this is really the data that global models need. If you're an agency running a local numerical prediction models or any type of other model, flood prediction models, whatnot, this is really the missing piece to make your models much more capable, much more accurate, much more successful. And the beauty is that it's already there. There is no need to launch new satellites or invest material amounts in getting this infrastructure built. We have already done it. And today, and this is really a cool statistics to see, roughly 70% of, at any given point in time, 70% of the sounding of the most recent soundings from Earth come from Tomorrow constellation. So this is a pretty impressive way to show how much more data we're adding to the global ecosystem of data. And zooming out on the Tomorrow offering, we start with data, but of course we don't end there. This is really just the beginning. We provide AI-powered weather modeling system and agentic AI business intelligence. We will not talk much about these two components today, but of course, if you're interested to learn about them, we welcome you to talk with us and get much more into the details about those as well. And I will wrap with this really cool animation, which is showing roughly 2 days of data collected from our constellation in the recent few weeks. And you can see how from the start, within really short time, we get full coverage of the entire Earth. And then we can see all these different weather systems moving. You can see the tropical cyclone here next to Guam. And you can see the cold front in the northern US. And all of this is solely from our constellation. So this is an incredible depiction of the quantity and quality of data that we're capturing. So with that, I'm again very excited to have you join us in this webinar, and I welcome you to participate, ask questions, and engage with us. Thank you so much.
Hi, I'm Joe Munchak. I'm the Vice President of Mission Science here at Tomorrow.io, and I lead our Mission Science team, which is a group that's tasked with producing the data products from our satellites and ensuring that these products meet the highest possible accuracy and lowest possible latency. So today I'm going to be talking about the Tomorrow.io microwave sounder constellation, the mission as a whole, and where it fits into the ecosystem of other satellite missions that operate at similar wavelengths. So I'm going to spend a little bit of time first talking about the technical specifications of the Tomorrow.io microwave sounder payload. Then I'll talk a bit about our constellation as a whole and the coverage that it offers and how that's enabled by the different orbits that we fly in. We'll dig into some details about how the instruments have been performing now, in some cases with over 1.5 years of data from space. And then I'll do a deep dive into the data products that we offer from these satellites. So first, what is TMS? It's a 6U CubeSat microwave sounder, and you can see an image of it here in the middle. It has heritage from a NASA-funded science mission called TROPICS. That was the first CubeSat microwave sounder that was intended for a rapid revisit of tropical cyclones. So that was in a 3U, which is about the size of a shoebox. TMS has doubled that size, which has given us some space to put on additional calibration targets, as well as improve some of the electronics in the receivers to get a more stable and accurate temperature measurements in particular. So it's an advancement of this already high-tech NASA design, and we've launched 11 of them to date and continue to build more as we prepare for the future constellation launches. So at this point, some of you may be curious what exactly a microwave sounder measures and how it differs from conventional weather satellites. So you can see here the electromagnetic spectrum ranges from radio waves all the way to ultraviolet. And weather satellites conventionally measure in the visible and infrared portion of this. So here's an example of a GOES visible satellite image over the United States and the Atlantic Ocean and South America. And this is where we typically see the cloud patterns and surface and dust and haze also shows up in some channels. The geostationary satellites also offer water vapor channels that use infrared wavelengths. And so what you see here now are water vapor patterns at mid-levels of the atmosphere, as well as the same cloud patterns that we saw in the visible image. Finally, the traditional imagery uses what are called window channels in the infrared. These are slightly longer wavelengths that aren't sensitive to water vapor, but allow us to see down to the surface temperature if the sky is clear, but if there are clouds, all that you are really seeing here is the cloud top temperature. And so the bright colors here indicate clouds, and the darker colors are the warm surface. So when you go to the microwave, that's quite a big step in frequency now. We're talking about a factor of 100 or more in wavelength increase. So now what's happening is that the wavelengths are much too large to interact with the small cloud particles. So instead, we're seeing through the clouds and we're seeing other features. Microwaves are also sensitive to water vapor, but this is now water vapor without that cloud impact that, like we saw with the geostationary imagery. And so now we're seeing the water vapor patterns underneath those clouds, and we're seeing the precipitation cores within the convection. Those are those bright colors that you see here. And finally, we also have window channels in the microwave. Those see down to the surface. There's much more land-ocean contrast in these, so we can see that land-ocean boundary distinctly. We can see water vapor patterns over the ocean with this quite clearly, and we can also see that precipitation signature. And this doesn't even showcase the temperature profiling capabilities that these channels have as well. But TMS has 12 different channels that were specifically designed to measure temperature and humidity at various levels of the atmosphere, as well as see through to the surface in those window channels. So we can sense surface temperature as well as the cloud and precipitation properties throughout the depth of the cloud, not just the cloud top. The TMS constellation, as I mentioned before, consists of 11 satellites that have been launched to date. These have been launched into 6 different orbital planes that provide us round-the-clock coverage. You can see here, this is an animation composed of 3 hourly snapshots, and you can see that we have these distinct clusters of data. Those are the different orbital planes that we fly in. When you take all this data and count how many individual passes a TMS satellite has over any given location, and do that, average that by latitude, that's what I'm showing here on the right. That's our zonal mean revisit rate, and you can see it's about 1 hour on average. So we have a 1 hourly average revisit rate. And then in some places, it's a little bit worse. In some places, it's a little bit better. It depends on the nature of the orbits and how many overlaps we have. So right around 45 degrees, we have some orbits that are in that inclination. So there's a little bit more frequent coverage there. And again, right near the poles as well. With our polar orbiting satellites, we have better coverage there. But overall, it's about 1 hour average revisit rate. And this happens at certain times of day because of the orbits that we launched into are what are called sun-synchronous orbits. So those ones, satellites always pass over at the same times of day. Those are the straight lines on these plots, and they happen around 11 a.m., 11 p.m., and about 5:30 p.m. and a.m. At any given location. We also have those 45-degree orbits that those ones change the time of day that the satellite passes over a given location on about a 60-day repeat cycle. So the combination of these offers the hourly average revisit with minimal gaps in between passes. And finally, we didn't design TMS to operate in a vacuum or as a standalone mission. It's designed to complement government-operated backbone sensors with rapid revisit. And so if you were using just the government agency-operated satellites, such as the ATMS instruments on NOAA satellites or the European Meteorological Satellite Agency's MEDOP series, along with some research missions from NASA and JAXA, you would get the coverage you see on the top panel. On a 1 hourly basis, there's large gaps. The satellites tend to occupy those same few specific planes by the operational missions, and other times of day don't have very much coverage. But when you add TMS to the mix, now we're covering the vast majority of the globe, even in a 1 hourly time frame. And the most recent data at any given point most likely comes from one of the TMS satellites. So it's great that we have this coverage that is on par with the ones operated by government agencies. But how did the instruments perform? After all, a poorly performing instrument will not provide as valuable data. So we have taken great care to, first of all, perform accurate calibrations as well as validate our data against many different independent sources. So for a microwave sounder or any microwave radiometer, there's an intrinsic measurement of the instrument's noise. That's called the noise equivalent delta temperature, or NEDT. And this is just the basically pixel to pixel noise level that we observe in that instrument, how much variation there is if they were looking at a purely uniform scene. Then for the validation, we see how well the measurement is comparing to what we would simulate from that other validation source. So we have, if we wanted a validation everywhere, we would use a model reanalysis. So this is a model's estimate of the state of the atmosphere that we can simulate our measurements from. And That model is not going to be perfect because it doesn't have measurements. It's not assimilating TMS data, so it's relying on numerical weather prediction to propagate the state of the atmosphere properly. And so there is going to be some error. It's never going to be a perfect match. In particular, it doesn't handle clouds very well, so we do screen out clouds from these analyses. And depending on the channel, some channels we're getting very close to the NEWT. Other channels that are more sensitive to clouds and water vapor don't do quite as well. So that's what you see in the orange bars there. But another thing we can do is validate against other satellites directly when our satellites pass over a location at the same time as these other satellites. So we've picked two satellites that are known in the community to be very well calibrated. Those are the ATMS instrument aboard the NOAA polar orbiters and the GMI instrument on NASA's GPM mission. And these have a handful of direct equivalent channels to TMS that we can compare directly. And what we see here is that the TMS measurements are closer to the other satellites than they are to the reanalysis, which tells us that we're observing a state of the atmosphere that has information that the reanalysis doesn't have. So we should be able to improve forecasts. Finally, we also use radio occultation profiles, which are very good at measuring temperatures in the upper troposphere and stratosphere. And we also find there that we see similar or better performance of TMS compared to those instruments when we compare it to ERA5. So on the whole, we're seeing that the data quality is good. In many cases, it approaches the noise level, and even in channels where the scenes are very complex and have a lot of clouds and water vapor features that aren't well represented in the models, we still measure other satellite or compare to other satellites better than we do the reanalysis. We also look for things like biases with respect to latitude. Those tend to be very small, as you can see in this image from some of our newly launched satellite, TMS-10. And also across the dynamic range from cold scenes to warm scenes, we don't see any trends there. We mostly line up right along that one-to-one line when we compare to ATMS and the channels that we have in common. There's a lot more detail on this in this publication that's now currently in a revision and review stage, but a preprint's available online at this link. We've also had some independent validation. This particular comparison comes from Professor Mitch Goldberg at CCNY, and he took an approach where he took our data and matched it up to the ERA5 reanalysis and then attempted to retrieve the state of the atmosphere on an independent time period just based on the information that was present in the TMS channels, noise and all. And he did this not just for TMS, but also for ATMS and the Arctic Weather Satellite, or AWS, which is the prototype satellite for the EPS Sterna constellation, which is another microwave sounder constellation that won't come online until the 2030s. And what he found was that, first of all, ATMS is the best performing of the three. We see the lowest error there. But ATMS, of course, has many more channels and lower noise per channel, so this is not expected. It's a much larger class of instrument. What he also found was that TMS compares favorably to AWS, both in temperature and humidity, or at least equivalently, despite being a much smaller form factor. And again, TMS has a constellation out there now, whereas AWS and EPS Sterna won't be around for another 4 or 5 years. So if you're interested in our data products, we have a whole suite of level 1 and 2 data that contains the brightness temperatures. It's all processed through Argo Workflows, which is a data pipeline system that operates on Kubernetes clusters through various cloud compute providers. And it's automated every time we get a downlink from the satellite. We produce these products and deliver them, usually within 10 minutes of receipt of the L0 data. So I'll walk you through our level 1 products here. Our fundamental or lowest level of level 1 product is 1BTB that contains the antenna and brightness temperatures at the native sensor sampling and geolocations. So you can see there a typical scan pattern. The antenna temperatures are combined into a brightness temperature after some antenna pattern corrections are performed. We also have a 1BTBR product, which is where all the channels are resampled to a common geolocation. This can be useful for applications that require each channel be at the exact same center location. And finally, we have a 1CTC product, which is the same sampling as 1BTBR, but now we are converting everything to a common spectral response. So all the different TMS instruments look identical after they've gone through this intercalibration process. We also have a 1CTCR, which is a spatially resampled 1CTC. And you can see here the difference. The native sampling, even with the 1BTBR, has the typical scan pattern that you see from a cross-track scanner, where the footprint spacing is wider apart at the scan edges than it is at the center of the scan. And so what we've done with TCR is resample so that all of the pixels are equally spaced apart on the surface. And this is particularly useful for image-based machine learning applications such as UNets. We also have a field in this product that performs what's called a limb adjustment, which is where we remove the scan angle dependence of the brightness temperatures by applying a neural network limb adjustment algorithm. You can see here what's been done with this image is that there's this channel is always colder on the edges than it is near the center of the scan because the edges are seeing higher in the atmosphere where it's colder. This is a temperature sounding channel, and so we've managed to mix the channels in such a way that you're looking at a uniform height response, and so you see uniform temperatures across the scene, and any variations that are there are due to actual changes in the temperature of the atmosphere, not just changes in the scan angle. We also produce level 2 products. These are intended to get back the state of the atmosphere from the measurements, and so we're retrieving temperature profiles and humidity profiles, as well as a few integrated cloud parameters such as ice water path, liquid water path, precipitation rate, and storm top height. And these products are also available. And again, we've validated them, and they compare very similarly to products from other microwave sounders, such as the MIRS product from ATMS. Finally, some users may be interested in gridded data that's on a uniform latitude-longitude grid. So we have started producing a level 3 gridded ZAR product. ZAR is a cloud-native data format that allows for ease of access and subsetting along any of the dimensions of the array. So in this case, the dimensions are time, latitude, longitude, channel, and satellite. So you can sample the entire TMS data record by querying against this. And here's some example applications looking at one satellite at multiple times throughout a day, or multiple satellites within the same hour, or even performing very short-term time differences of brightness temperatures to look at convective growth and decay, which is something that can only be done with a constellation like TMS. So thanks for your time. I hope that this has whetted your appetite for interest in the TMS data. I believe the next speaker in this webinar will be Ryan Honeyegger, who's going to dive into more of the applications of TMS. Thank you.
So, hi everyone, I'm Ryan Honeyegger, and I lead the numerical weather prediction division at tomorrow.io. Today I'm going to talk to you a little bit about how we can use the Tomorrow Microwave Sounders, or TMS, in a few different applications. So, to recap from Joe's talk, TMS represents a series of small satellites in several low Earth orbits that collectively provide global sub-hourly coverage. This enables rapid refresh applications and greatly helps with any other activity that benefits from large amounts of satellite data. But how do you actually use TMS in those applications? Many of your applications will be agency or organization specific, but they do have a few common patterns. Our science staff are developing many different reference examples that can speed up your own evaluations and integration. So let's start with some overpass applications and a little bit of nowcasting. And for this, let's just look at tropical cyclones a bit because they're always wildly fun. So TMS is primarily a microwave sounder, and by virtue of being a microwave sounder, it allows us to peer inside of clouds and infer vertical profiles of temperature and water vapor, and you can even retrieve precipitation properties to a certain extent. So TMS sounding channels have sensitivities that peak at different heights in the atmosphere and even at the Earth's surface. So just from a colorimetry perspective, we can assign colors to these and create composites to show details of storm structures. So here is an overpass of Typhoon Sinlaku, which was a Category 5 tropical cyclone which impacted Guam earlier this month. The swath here is about 2,200 kilometers across. So our window channel composite in the center shows precipitation, convection, and areas with low humidity. The composite to the right presents a view of moisture in the upper troposphere, which is also shown alongside a proxy for storm top heights. TMS can resolve brightness temperature anomalies, and it can even infer the warm core structure of the storm. So diving in a little bit deeper, let's just say it's a lot of fun to watch sequences of microwave overpasses as storms evolve. Here's another recent example from Cyclone Narelle, which had 4 separate landfalls over Australia. I think this might actually be the record. And over 10 days, TMS had 84 direct overpasses that resolved the full cyclone, and they occurred at all different times during the day. Now, that's actually comparable or similar to the total number of overpasses from US-based and EUMETSAT-hosted sounders, but given the orbits of the satellites, TMS observations do tend to be very evenly distributed, whereas for the US CubeSat constellation, the observations do tend to be clustered at particular times of the day. And you might wonder why that is. So here's what I mean by this. Here are two different views of where our satellites are positioned versus other satellites in the observing system, and this provides a little bit of context of why TMS satellites are very useful. Most microwave sounders have historically been launched into sun-synchronous orbits, and that means that these satellites pass over the same points on the ground at the same times each day. To the left is a clock plot which shows the equatorial overpass times in UTC. You can see, based on the satellites, sometimes they look like they're clustering around 2 or 3 orbital planes, and that's really what's happening here. Now, TMS has that too. We're matching common orbital planes for cross-calibration, but in addition to this, TMS is also deployed in inclined orbits that precess each day, and they fill in the gaps inside of the observing system, so we always will have overpasses. So the various satellites do strongly complement each other, and since we always have a recent microwave overpass, we can peer inside of clouds, and our precipitation estimates should always exceed scale from geostationary-only observations. And that's what I'm going to highlight here. In one of our recent papers, we showed the development behind our nowcasting algorithms. We're able to fuse microwave and geostationary vis-IR observations to improve precipitation retrievals. Traditionally, these have only been done through geostationary observations because it's very hard to have a low Earth orbiting satellite pass over a cloud at the right time and have enough overpasses to make a robust retrieval and see how precipitation is evolving. By adding in microwave, you can not only see inside of a cloud structure and get a better precipitation retrieval, but with a rapid refresh microwave constellation, you can do this all the time, and you can establish a bit of a time value behind our observations. For TMS, that time value is about 70 minutes, which means that our high key skill scores for precipitation forecasting are exceeding those of a geostationary only retrieval for about 70 minutes post-observation. Given that our global median revisit rate is now sub-hourly, we actually now have large periods of times for any storm system where we never have to fall back to pure geostationary skill. So we're able to make a better precipitation forecast, we're able to make a better nowcast with these satellites, and ultimately we can produce better weather insights. Now, beyond precipitation detection, I'll highlight SIMS at the University of Wisconsin, and they are estimating tropical cyclone intensity using data from TMS alongside other microwave sounders. That team runs a public-facing operational website that tracks cyclones globally, and TMS data already account for half of all observations. That helps greatly with catching rapid storm intensification events, which in our evolving climate happen with increasing frequency. And I'll say that this study is ongoing, and we're excited for future developments in the upcoming Atlantic season, which is about to start. So let's also talk a little bit about data assimilation. This is one of those capstone integration activities, and TMS really is a sounder that's tailored towards temperature and water vapor retrievals, so data assimilation is a great application because of that global coverage and its decent calibration. So there's many different possible ways to assimilate TMS into a model. Scientists have historically taken clear sky approaches. There's been some recent development in the all sky community. There are frequent discussions about thinning and super-opping, which really from a certain point of view is a type of averaging, and on developing appropriate quality control methods for the observations and developing appropriate bias correction models. My group has a recent paper published in QJRMS that describes the methodology behind one approach to accomplish this, and it's intended to be a reference for the field to accelerate uptake. So what does that mean? Say that you're a small to mid-sized satellite agency and you want to investigate TMS. This acts as a potential starting point. And to do that, we've aimed for maximum applicability. We built this reference using the Joint Effort for Data Assimilation Integration, or JEDI, which will power operational data assimilation at many different agencies, from the US-based ones through the UK Met Office and beyond. It's starting to roll out into production just now. And JEDI works with the FE3 model, it works with MPAS, LFRIC, many others, and it also supports common observation operators like the Community Radiative Transfer Model, or CRTM, and also RTTOF. With JEDI, we can convey the instrument science has a set of human-readable configuration files instead of as machine code. So you don't necessarily have to have a software engineer looking at the code trying to work out what it does. An actual scientist can take a look and can understand how and why this assimilation method is working. So as part of the study, we actually build up a cycled reference system that is loosely paralleling NOAA's Operational Global Data Assimilation System, or GDAS. And it's designed to provide a simplified baseline with the resource requirements that are within range of a mid-sized academic or a small government agency. That being said, it is ingesting real observation data from NOAA's observation processing system, and it does also rely very heavily on the Environmental Modeling Center's efforts to migrate to JEDI from the GSI code. It's using the same non-TMS instrument configurations. It's just using a more simplified data assimilation setup. And as part of this experiment, we developed the TMS assimilation by following a fairly standard methodology. We're using an innovation-based diagnostic scheme to approximate TMS's observation error variances, and we do this on a per-channel basis. We establish clear sky filters, and then we also establish an all-sky model using an approach that was originally designed for the infrared community, but is seeing increasing application in the microwave field. For details here, see our paper. We do have a set of experiments, and we are basically running data denial cases from some control. Our control has all available observations in our observing system, both TMS and non-TMS. And then for data denial, we're removing microwave observations from different satellites to establish the impact. So for example, we can take our control and remove 2 TMS satellites. We can also take the control and remove 2 instruments of any other system, including, say, the Advanced Technology Microwave Sounder, or ATMS, which is the flagship microwave instrument that NOAA has deployed up till present. So we're considering small numbers of data denial cases, but it's enough to establish some trends. So here are 2 plots of 6-hour forecast impact. The temperature is on the left, water vapor is on the right, and I show here both TMS and ATMS data denial cases. At first glance, you can see that the instruments are comparable. And by that, what I mean is that they behave similarly, and they behave in a very physical manner that reflects their underlying build characteristics. You need that consistency. It's really important, and establish some expectations for performance. So the ATMS instruments, so the Advanced Technology Microwave Sounder, are much larger. They have a larger sensor, they have lower noise, they're designed for a very robust build, and in particular for temperature channels, they're looking at lower spectral frequencies than what our TMS instrument is looking at. So that means that the footprints are a little bit different, and the bandwidth per channel is a little bit different, and you can see how this comes through for temperature. Still, TMS does have some temperature impact, particularly where there are no ATMS observations, because again, it's only in one orbital plane. For water vapor, however, you can see that we're actually much closer in terms of performance, and this reflects fundamental physics. Our footprint sizes are very similar, the bandwidth is very similar, and so is the fundamental instrument noise. So you can see that TMS establishes a very similar impact across your troposphere. Our impact skews a little bit higher because our sounding channels have slightly higher peaks, but that's also physical, and the overall impact is what we expect, especially given our calibration studies and external evaluations. So we can run this out for a few days to gauge if the impact still persists, and it does. Here are TMS and ATMS data denial cases at different lead times and pressure levels, and you can see that the behavior is what we expect. Impacts are significant out to around 3 days, after which our own error becomes more dominated by model level effects. Again, we're running a more simplified data assimilation system, and that is totally expected, but in an operational setting, we expect this impact to persist a little bit longer. Now, you might wonder how we're validating all of this and how the observations and instrument science can be integrated into your systems. So, 2 different things here. First, we have several recently published papers that have some bearing on the subject. Joe Munchak's paper is in preprint, and this first one discusses the TMS pre- and post-launch calibration procedures, and it discusses calibration accuracy in terms of geolocation error, and it also discusses radiance validation, where we look at bias and we look at the standard deviation and other noise characteristics like NEDTs. This establishes our performance expectations. Outside of that paper, we have considerable material describing each satellite's calibration status. Garrett et al., our second paper here, describes that all-sky assimilation approach, and it presents the impact study that I briefly walked through. There's a lot of content there. It's an open access paper. We again hope that you'll be able to find a lot of insight from this. Forrest Cannon's paper establishes our precipitation retrieval algorithms and discusses that time value of observations and overall skill. Beyond this, we do have many other white papers, many other presentations available both internally and externally, and we also are working on several new manuscripts that should be entering peer review later this year. Beyond just our own publications, there are some independent evaluations that are either ongoing or have recently concluded that I can highlight. So the first of these is the NOAA Commercial Microwave Data Pilot. The goal of this pilot is to integrate our sounders into relevant NOAA workflows and products and to assess their performance. So for this pilot, we have delivered data from several satellites for many months now, and this is real-time data delivery as soon as we acquire the data from the satellite, so as soon as we downlink. So observations flow to NOAA, and then they can use them in systems like the Microwave Integrated Retrieval System for assessments. They've used them with AWIPs. They've used them in other places too. NOAA does sponsor a very large evaluation group composed of scientists from several national and international agencies. So other groups have access to the satellite data as well for the purposes of this assessment. Now, I'll say that the evaluation is still in progress and NOAA's conclusions are their own, but NOAA staff have given many public talks recently. An overview was presented at this year's annual AMS conference by Sherry Pan. I have the citation down below, and we're looking forward to the release of any final reports. Beyond that evaluation, the Joint Center for Satellite Data Assimilation, or JCSDA, also conducted their own independent evaluation for the U.S. Air Force. This is the same group responsible for core JEDI development, and they assessed 4 TMS satellites over a 6-month period using primarily the model for prediction across scales, or MPAS, and also a little bit of FE3. So they assessed a few data assimilation configurations, one of which was very similar to what we proposed in our paper, and they also noted a robust increase in forecast skill. There are other ongoing DA studies at NOAA, NASA, and other agencies, plus several for the preceding Tropics instrument, and we can provide more specific updates on request, but overall, we think that TMS is doing very well, and TMS impacts or TMS-like instruments will become a mainstay in the global observing system. Anyways, thank you for your time.
Hello everyone, my name is Cesar Benetti and I am a solutions engineer for Tomorrow I/O. We heard from our science team about Tomorrow I/O microwave satellite constellation, technical overview and applications. Now, let's talk about data access and support. First, for individual access. From our webpage, you can access sample level 1 and level 2 data from our satellite constellation. These are sample data for individual users to understand data format and content provided from each product. But we also provide data access for research purposes. In this case, you have access to archives data for a specific time period and spatial domain. In the web page, you can submit your request, which will be evaluated on a case-by-case basis. You will receive an email about the review process and how to access the data that was requested. Now, let's talk about government agency access. The government agency access starts with the agency engagement with a discovery meeting, including scientific briefings with the support of our science team. In these meetings, you'll be able to provide more detailed information about the satellite constellation, data definition, and usage. The next step is the actual data access request. We will have a NDA or MOU signed for the trial request, and we will start defining together the specific products, spatial domain, and data format. The products could be level 1 or level 2 data, and the domain, for example, global or regional data access. We provide satellite data in multiple data formats, usually as NetCDF files, but we can also provide other WMO standards if required. Then we go to the trial data delivery, where we define data access and provide documentation and technical onboarding. The access can be provided either as API endpoints or cloud data buckets, such as S3, where the agency is able to pull data as previously specified. During this whole process, we will provide the necessary technical support as well. Then, during the integration and evaluation, the agency will already have the data available for their data simulation pipeline into their numerical weather prediction models. At this step, the government agency will be able to run their validation and accuracy measurements and also evaluate the impact of our satellite in their models. During this process, we will also be providing the necessary support for their agency technicians and scientists. Then we'll go to production and automation. When we'll have a service level agreement for data delivery defined and in place, and at this stage, everything is scaled and with a stable pipeline. The agency will have by now an automated process for real-time data ingestion in their data assimilation system. And with the system in place, it is ready for our satellite data operational use, when the agency is able to use the satellite data for their own weather nowcasting, forecasting, and early warning systems. The onboarding process starts with the introduction call with our science team. Then the support for definition of the area of interest, if regional domain or global coverage, a definition of the satellite products, such as level 1, level 2 data, and data formats, if NetCDF or other, and then the definition of the data delivery, such as API or Cloud Bucket. We can also provide support for data assimilation configuration, such as JEDI, the Joint Effort for Data Assimilation Integration System from the JCSDA, and we also provide calibration reports on requests. We can provide upon through the whole onboarding process, enablement support as well. More information is provided on our Data as a Service user guide with completed in detailed documentation of our data and how to get access to it. Also, more information about our service level agreement, including availability, support commitment, responsibility, and accountability. All this documentation is accessible through Tomorrow.io website. In our webpage, it's very easy to access our satellite data. You can go here on the tab, select Data Catalog, and in this catalog, you will see a brief description of each file, each level 1, level 2 data, with more information here, and you are able here download the sample data. Easily submitted, and then you get the data here. Or you can also go for a more data discovery for research purposes, where you can select here in this web page the sensor, for example, the microwave sounders. You can select one or more level 1 or level 2 data here. And you can select the time period of the data. Remember, this is archive data only. If you would like to request the worldwide data, you can, or you can also get a different location, very easily moving this icon here, and we'll find the data. Once you select the area, the products, and the period, you will fill this form and submit it for our analysis.
Thanks, Caesar. Hi, I'm Ari Davidoff. At Tomorrow.io, I work on with national agencies all over the world on satellite data programs. Let me focus the last few minutes on what this looks like from your perspective as an agency thinking about working with us. At a high level, what we deliver is not just data, but a combination of data, technical integration support, and mission-specific capabilities. That starts with operational data services, continuous real-time delivery of satellite observations. It extends into technical enablement, supporting agency teams in integrating and using that data effectively. And where needed, it can expand into more tailored solutions built around a specific operational need. The goal across all of this is to support a path from initial evaluation through to full operational use. At the core of all this is, of course, our data as a service offering. This provides a direct access to the underlying data products, both calibrated observations and high-level retrievals. The focus here is on an operational usability. The data is typically delivered via bulk file transfer in globally accepted formats for integration into production pipelines. This is typically the starting point for most agencies, assessing the data and integrating it into their operational workflows. Beyond access, a critical part of the engagement is technical enablement. For most agencies, the challenge is not just getting the data, it's using it effectively. We support teams with integration into their existing systems, including data assimilation workflows and system optimization. Just to be clear on scope, the agencies continue to use and operate their systems. Our goal is to provide expertise
to help get the most value from that data. In terms of how this is structured commercially, we keep the model intentionally flexible. Different agencies have different requirements, whether that's operational forecasting, research, or both. Engagements are typically structured based on agency's use case, the scale of the data it needs, and how broadly that data needs to be used within the organization. Some agencies engage purely on a data access basis. Others combine that with technical collaboration. And in some cases, we structure more integrated packages. The goal is to align with the agency mission and enable long-term adoption. One area that's often important and sometimes less visible is how data licensing is structured. Our framework is designed first and foremost around government use globally, with national agencies as the primary users of the data. A key distinction we make is between operational and research use. Operational use typically involves real-time continuous data for forecasting and decision-making, while research use is more focused on archived data for analytics and scientific advancement. We also structure licensing to be flexible in terms of how broadly data can be used, whether within a single agency, across multiple agencies, or in collaboration with partners. The goal here is to strike a balance. On the one hand, making the data accessible and usable for agencies to fulfill their missions. On the other, ensuring the long-term sustainability of the data and the broader ecosystem that supports it. So this is something we typically tailor in collaboration with each organization, depending on their specific requirements and use cases. The question that often comes up at this stage, how is this service actually priced? At a high level, we don't use a single fixed pricing tier. Instead, pricing is structured around the mission requirements of each agency. There are a few key factors that typically drive it. That includes the use case, whether the data is being used for operational forecasting or research. The scope of the data, including coverage, volume, and latency requirements. The level of access and licensing, meaning how broadly the data is used across the organization or with partners. And the level of support or integration involved. So rather than a one-size-fits-all model, engagements are scoped collaboratively based on what the agency is working to achieve. Contact us and we will work with you on informing your budgeting process. Another question that often comes up is, what if I'm an individual researcher without direct funding? Our approach is to support the research community in a way that scales. In practice, most access is coordinated through national agencies and funded programs, which allows data to be distributed more broadly and sustainably. For individual researchers, the typical path is to engage through those institutional channels and align with larger programs. In select cases, for example, high-impact validation work, we may support direct access, but the overall model is designed to enable science through these coordinated pathways. A direction we're moving towards, and this is a meaningful shift, is adding a managed service layer on top of the data itself. This goes beyond delivering data sets. It introduces a policy-driven, secure delivery layer where how, where, and when data is accessed is governed as part of the service with built-in access controls and compliance to specific standards. At the same time, this becomes an integrated mission-aware capability, combining data, processing, and system-level integration into something that's tailored to the operational environment. And importantly, it's delivered as managed infrastructure. That means defined performance characteristics around latency, uptime, and resilience, with centralized oversight and the ability to deliver in distributed or constrained environments. So the shift here is from providing data to providing a controlled, mission-ready service layer around the data. So in summary, for agencies, in terms of the next steps, engagement with Tomorrow I/O is typically straightforward. We start with predefined access and onboarding, setting up data delivery into the agency's environment. From there, agencies move into evaluation and validation, testing the data within their systems and measuring the impacts. And then, where it makes sense, scaling it into operational use. We support that progression at each stage. With all that being said, now the team here would be happy to take questions, and we'd be glad to continue the conversation after the session.